In this video, we prove the Parseval-Plancherel theorem, which we stated last time. So the proof is a bit technical, I'm afraid, but I'll try to guide you through it as painlessly as possible. So what was this theorem about? Let's repeat it. We had a probability measure, mu, and we denoted its Fourier transform by phi. And we had a C2 test function h. And then what we want to prove is that if we integrate h with respect to d mu, then it is the same as 1 over 2 pi times the integral of the Fourier transform of h, complex conjugated, multiplied by Fourier transform of mu, which is phi. So this is what we want to prove. Now, since we remember what means what, I'm going to erase this part and just keep the formula somewhere so that we remember what we aim at. Okay, so proof. First, we actually need to explain why the expression on the right-hand side is integrable at all. We know these integrals, this integral makes sense, but why does this one? This is because the function phi is bounded by 1. So let me start by saying I'm trying to prove that h Fourier transform complex conjugated times phi is integrable with respect to dt. Since phi is always bounded by 1, that's true for every Fourier transform because we obtain it by integrating e to the power it x with respect to something which integrates to 1. So phi is always less or equal than 1. And we also know that the Fourier transform of a C2 test function is integrable. We proved it in video 25, so in the last video of term 1. So this one is integrable. So therefore the product will be integrable. Okay. So now when we know that the right-hand side makes sense, I'll start with the right-hand side and I'll try to get to the left-hand side. So I'll start by writing down the expression on the right-hand side, 1 over 2 pi, the integral from minus infinity to plus infinity, h hat t bar, phi of t dt. And in the next line, I'll do two things. First of all, I will replace the integral from minus infinity to infinity by the integral from minus t to t and send t to infinity. This is so why I want this integral to be finite, because in the next step, I want to apply Fubini's theorem, and it will only be applicable if the interval of integration is finite. So I'm going to say limit of the integrals from minus capital T to plus capital T as t tends to infinity. And then also I will simply substitute the definition of h hat and the definition of phi into this formula here. So I'll start with h hat. So the definition of h hat is that it is the integral from minus infinity to plus infinity of e I t x h of x dx. So that would be h hat, but I also have bar, which means I need to take complex conjugate. Then I just observe that h is real, and this means I only have to conjugate this term, and this term can be easily conjugated by just replacing plus sign with a minus sign. So that's the h term, and now the definition of phi is also the integral over r e I t. I need to use a different variable because x is already taken for the previous term, so I'll say y d mu. And just simply to integrate that my integration is over y, I will write the parameter y next to mu, but it means nothing. It simply reminds us what the name of the variable is. And then I shouldn't forget to put dt, because my first integral was over t. Okay, so now I want to apply Fubini, and we will see why finiteness of minus tt is important. So Fubini, okay, so I keep the limit, I keep the factor 1 over 2 pi, but now Fubini tells me I can swap limits, and the order in which I want to get my limits, my integrals are, first I want to have the integral over r, then I want to have the integral over the other r, so from minus infinity to plus infinity, and the last integral will be with respect to t, and then I notice that actually this, so the function which I will be integrating will be this one. And I notice that the h part doesn't actually depend on t, so I can already write it in front of the integral, which is going to be with respect to t. So I'm going to write h of x, and then I'm going to write the last integral, which is from minus t to t. And in that last integral, I will have e I t y minus x dt, and then dx, and then d mu y. Now, why is Fubini applicable? First of all, this term is bounded by 1, so I'm thinking about this term as 1. Now, this term should be integrable with respect to dx, which it is because h is a compactly supported function. Now 1, so the upper bound for this, should be integrable with respect to d mu, which it is because mu is a probability measure, but it also has to be integrable with respect to dt, and the function y will only be integrable with respect to dt if the interval of integration is finite. This is why I needed minus t here. But it is now finite, so Fubini works. Let me put it here. So Fubini. And now, in the next step, I'll do two things, or maybe three. So first of all, I will, so the main step which I will make is I will actually compute this integral here. So let me write it somewhere. So this integral will be e I t y minus x divided by I y minus x from minus t to t. So you see, if I borrow a 2 from here and put it over here, then and substitute t and minus t into this variable, then what I will have from this term, together with a 2 which I have borrowed, I will have sine I capital T y minus x, and I will also have 1 y minus x in the bottom. So this is what I'm going to write down now. So first of all, I will put the factor 1 over 2 pi inside the limit. Actually, all even in front of the, so inside the first integral. Since I'm borrowing 2, I will only write 1 over p. Then I will write the second integral from minus infinity to plus infinity h of x. And then I will write down the result of the integration here, which is just this simple calculation, and which will give me sine t y minus x divided by y minus x. So I should have written okay, no, y minus x is correct, but what I'm going to do, I'm going to observe that sine is an even function and this is an even function, so I can change both y minus x to x minus y and nothing happens. And this will be slightly more convenient for the future, so I'm going to replace this by x minus y. So x minus y here, x minus y here. And then don't need this part anymore. So I don't have integration with respect to dt anymore, but I have dx d mu y still. Okay, so here we are. This is the right-hand side with which we started, and we got something which looks pretty scary. What we want it to look like is this nice integral. So let's see how close we are. So this integral is over R. Here, this external integral is over R as well, with respect to d mu, very much like this integral here. So if only I could prove that this function here, this one, converges to this function h, so h of y, in a nice way so that I can use the dominated convergence theorem, then I could simply say that the integrals converge to the integral of h with respect to d mu as stands here. So it turns out that all what I need to prove is that this huge term converges to h of y, and since I want to use the dominated convergence theorem, I will have to prove that this huge term is also uniformly bounded. So before I write it down, let me give you some idea why this may be true. So if we look at this term here and try to draw a picture for it, so somewhere I have my point y, and so this function is a function of x, so y is fixed. So let's see, if my x is very, very, very close to y, then this expression, I can temporarily put a t in here and another t in here. So then we see that for very small argument, this ratio converges to 1. So it's roughly 1. So the size of the whole function here will be roughly t, so pretty big because my t tends to infinity. So this is of size t, and if x is quite far from y, then I don't actually need to be looking at this term this way, separating so t. I can simply say that sine is bounded, and when x minus y converges to infinity, this term converges to 0. So this function here looks roughly like this. So it's big, but then it's getting small, and then it fluctuates and tends to 0. So in a way, it looks like a Dirac measure at the point y. So Dirac measure is something which is huge at one point and almost non-existent anywhere else. And if you integrate the Dirac function with respect to any function, then what you end up with is the value of your underlying function at the point where your Dirac measure lives. So this is why, I mean, this is not a proof, we will prove it properly, but this is the intuition behind the proof. This is why it's plausible to believe that this huge integral will actually converge just to the value of h at the point y. Okay, so hope it wasn't too confusing, but if it was, the proper proof is coming. So we don't need this. We don't need this. We don't even need this that much. What I want to denote this whole term, which I'm integrating by h capital T, because it depends on capital T, of y. And we want to prove, we need to prove that, so two things. One is that ht of y converges to h of y as t tends to infinity. And the second thing we want to prove is that ht is uniformly bounded. So uniformly means by a constant which works for all t. Uniformly bounded. So after that, we just apply dominated convergence theorem to this limit. So after that, we use dominated convergence theorem to show that the limit when t tends to infinity, which is this limit here, of this integral here, so of the integral over r, of this function here, which is hty, with respect to this measure here, so d mu. Actually, here I don't need to write the argument anymore because we only have one argument left. So we just pass to the limit, right? We can say that it is the same as the integral over r, h d mu, and this is exactly what we have on the left-hand side. So I want us to agree that it is enough to look at this formula at ht and prove these two properties, 1 and 2. 1, that it converges to h of y, and b, that it is uniformly bounded. Okay, so what I will do, I will copy the expression for ht to the next slide. So this is ht y, and I will also, okay, so I won't copy the points 1 and 2 which we have to prove. Okay, so this is hty. What I want to do here is the following. I want to split this integral into two halves. So one will be the integral from minus infinity to y, and the other one will be the integral from y to plus infinity. And I will split my function ht accordingly. So what I will do now, so I'll paste this formula twice here. And I will say the first integral goes from y to plus infinity. The second integral goes from minus infinity to y. So the first formula will be denoted by h plus. The second function will be denoted by h minus. And you remember our goal, so the first one, was to prove that this converges to h of y. So instead, we will prove that this converges to h of y half, and this converges to h of y half. And also our second goal was to prove that ht is uniformly bounded. Well, instead, we will prove that ht plus is uniformly bounded and ht minus is uniformly bounded. And clearly, since these expressions are very, very similar, we will not do it twice. We will not do it for both functions. We will just do it for one of them, namely for h plus. Okay? So I am going to get rid of this function. I'm actually going to get rid of this function. Maybe I'm going to put our aims here. So first aim is ht plus of y converges to hy half, and second aim is ht plus is or uniformly bounded. Okay, so this is going to be a rather long calculation, and in this calculation I will use integration by parts formula. So my parts will be this one, and so one thing here, and so this was not part of my formula for h, right? So I have to fix this. Let me just go back to the previous slide. So the definition of h was from here up to here. So when I did copy pasting, I accidentally copied d mu there. So d mu shouldn't be there. So we need to remove it from all of our h's. So I can't remove it from what I deleted already, but let me remove it from here, and I hope it's clear enough that mu shouldn't be there. Okay, so this is our ht plus, and now I'm integrating by parts. So my parts are those two. So how does integration by parts work? I write the first function, and I write the integral of the second function. And I can't actually integrate it, so I will have to write the integral, which would be from y to x, which is the variable. And then I will have to replace the variable x in this function by something else. So let me do u minus y. So I have to substitute the limits y and infinity for x. Maybe to make it clear, because there are so many variables, let me say for x I will substitute y, and for x I will substitute infinity. So this is the first term. The second term is minus the integral from y to plus infinity of the derivative of the first part, which is h prime, times the second part, which is still this integral here from y to x sine t u minus y du. Okay, so du is also du is missing here, so I'm going to fix that. Let's move it over and add du. So now it's correct. Okay, and here I'm integrating, so I will integrate all the way over dx. Right. Okay, so let's see what happens when I substitute the limits into the first term. So when I substitute y for x, so y here, then this integral turns into 0 because it's integrating from y to y. So if I substitute infinity for x, then I can't say much about the integral, but h of infinity will be 0 because h is compactly supported. So all in all, we're saying goodbye to this term. It's just 0. And we are left with the second term only. So is equal to minus 1 over p, the integral from y to plus infinity h prime x. Okay, so I want to improve the next bit a little bit. And to do so, I will use the change of variables. So I will replace this whole variable by something called v. So my new variable v is t times u minus y. Okay, then what happens? I have integral when u equals y, this lower limit, v will be equal to 0. So this is 0. When u equals x, v will be equal to t x minus y. So this limit becomes t x minus y. Then I have sine v, that's easy. Then u minus y becomes v over t. So it looks like I have to write t here, but I also have du, so I would have something like t du, and t du is the same as dv. So this t term goes to dv, and instead of this, I can write just dv. Okay, so now let's look at all these terms here. So first of all, you remember we have the lemma for this term. And yeah, I have to finish with dx here. Okay, so we have our lemma for this term. When t goes to infinity, the upper limit goes to infinity, and this term will go to pi half. Okay, now this means this term will go to h prime x pi half, simply because h prime x doesn't depend on t at all. So if only I could use the dominated convergence theorem, I would then be able to say that the integral of this function converges. Okay, so I keep the factor, but otherwise I have the integral from y to plus infinity, and it converges to the limit, which is h prime x pi half dx. And if you look at this term, you see pi and pi clearly cancels. And then I'm integrating h prime. It's nice to integrate derivatives because they integrate back to their original functions. So what I will have to do, I will have to evaluate h at plus infinity and y. At plus infinity it is 0 because it is compactly supported. At y it is h of y, and I have 1/2 and I have the minus sign, which do the job for me and give me h of y half exactly as required. So all I need to do is to justify the use of the dominated convergence theorem. And to do so, I need to take this whole term here and prove that it is bounded by something, which is that it is uniformly bounded by something which is integrable with respect to the Lebesgue measure dx over y plus infinity. So I'll just copy this term. So h prime x, the integral from 0 to t x minus y sine v over v dv, and I want to bound it. And this is why I needed my lemma, which told me not only that when I write infinity here, my integral is pi half, but I also wanted to know that this term is bounded. So I bound it by a constant, which I call c, and I do nothing with this term, because this term is clearly, so first of all, it doesn't depend on t, so I found a bound which works for all t, and it is integrable with respect to dx because h prime is compactly supported, so it simply disappears outside a finite interval. So this is integrable since it is compactly supported. So this finishes the proof of the first part, and we have done most of the work to show the second part. So I hope that I can actually squeeze it into this last line here, because we need to show that this function is uniformly bounded, right? That's our aim. And we have this formula here for ht plus, and I'm just going to estimate to upper bound this formula somehow. So namely, I will use the same constant c for this term. So it's less or equal than c over pi. So pi is this one. Then I actually don't care that I'm integrating from y. I will replace my integral by a bigger integral, which goes from minus infinity to plus infinity. And I will replace h prime by mod h prime x dx. So you see, this is a finite number because h is compactly supported, so it's integrable. This integral will be finite, and this number doesn't depend on t, so it is a uniform bound. And this is the end of the proof of part 2, and therefore the end of the proof of Parseval-Plancherel theorem.